Hello everyone, and welcome to the second week of Module 3 on Graphs in Social Media. Before we get into class today, or lecture for this week, quickly to go over some logistics. Your project proposal was due on Friday evening. I will be reviewing those presently and getting back to you with comments and feedback so you can get started on your collection report, which is due in a couple of weeks. For assignment, so your assignment 1 is due this evening at 11:59. As we finish this module, this brings up assignment 2, which is now due on October 5th, which is, again, about 2 weeks from now. All right, so what is Module 3 about? In the first week, we talked about defining, extracting, and visualizing graphs. This week, we'll talk about influential nodes and communities, looking at understanding something about influence and how groups of nodes kind of stick together in some way in the data that we have. From last week, you should now be able to construct graphs from social media, describe different types of graphs, directed, undirected, weighted, unweighted, these kinds of things, and scenarios where they might be applicable. Different kinds of statistics and characteristics of graphs, like the degree distribution, diameter, these kinds of things. And then build visualizations of graphs using GEPHI or NetworkX or iGraph or some other tool. This week, we'll be doing 3 different objectives where we'll define centrality metrics and use them to identify influential nodes. We'll extract egocentric networks and other types of subgraphs from a network, and then we'll talk about identifying communities of nodes and graphs, which will help in the graph characterization and visualization aspects. As with last week, I have 2 pre-lecture readings. One is Fast Unfolding of Communities in Large Networks. And this is similar to how GEPHI actually identifies communities. So reading this, you'll get some insight into the mechanics of community detection, specifically or insight into how GEPHI does this. And then another paper from ICWSM, the International Conference on the Web and Social Media, about measuring user influence in Twitter, the million follower fallacy, and why just retweets is not necessarily a very good metric for influence. Where are we in terms of the larger view of the class? If we look across the class's learning objectives, we're solidly in the middle of this, looking at learning objective 3 and 4, where 3 were about implementing and analyzing graph algorithms for analysis, community detection, visualization, and other mining tasks. In fact, this module, Module 4, and Module 5 are all core to the 3rd learning objective. So from last week, we've talked about actually extracting networks of different kinds. This week, we'll talk about ways to embed community structure, extract community structure from your visualizations, and use that to make your visualizations more effective. For the 4th learning objective on mining and extracting insights from digital traces, so we have already talked about some network characterizations in terms of things like density. So here, that top left graph is much more dense than the other graphs. We'll also talk about different kinds of subgraphs, and we'll talk about influence today, about different kinds of metrics for influence. Last time, we talked about characterizing nodes and graphs and some important properties thereof. Things like degree distribution, paths, specifically shortest paths, diameter, and network density. So these things will reemerge today when we talk about different kinds of centrality. So last week, we defined degree of a node as the number of neighbors a node has, with this example where the Washington Post clearly has a higher degree than New York Magazine. We can be a little bit more specific here. So in an undirected graph, the degree of a node is the number of neighbors, just like we said. Another way of defining this is the number of incident edges. How many edges involve that particular node? Now, because in undirected graphs, the order of nodes in an edge doesn't matter, then these 2 values are the same. But when we talk about directed graphs, we have a little bit of a different kind of definition, where instead of looking at the number of neighbors, we need to be much more specific about the number of incident edges, because we can have an in degree, that's how many edges come into a node, and we can have out degree, how many edges go out of a node. And then we put these 2 things together, like here with Carlos Castillo, we have an in degree of 1 and an out degree of 1. The degree becomes the summation of the in degree and out degree, and we get 2. So again, it's the same sort of definition. How many incident edges are there? How many edges involve this particular node? But we can have 2 edges for every pair of nodes, right? Because we can have A connecting to B, and we can have B connecting to A. So for directed graphs, we talk about degree as being the sum of the in degree and the out degree. So what does this mean in terms of influence when we are talking about trying to understand what are important nodes in a graph? Does a higher degree mean more influence? Potentially yes, but maybe it's really only a question of higher in degree. So how many people connect into me? Maybe that's more important about my influence than how many people I connect to. Now in Twitter, you may think this is an intuitive kind of definition, right? Because I have control over how many friends I have, so I can go and follow millions of people. But I have less control over how many people follow me. So if a lot of people are following me, that says something about my influence, or at least how interesting or attractive I am to the Twitter population. So at least for Twitter, potentially the number of, or the amount of in degree is maybe more important for determining my influence than the kind of out degree. So we can talk about this in terms of examples, right? So I'm going to introduce some sort of fun examples and move away from the social media aspect and more into the social networking aspect. So if you've ever heard of the Oracle of Bacon or the Kevin Bacon game, it's this idea that Kevin Bacon is this pretty influential actor, and within just a few hops, it's very easy to get from any actor you can possibly imagine to Kevin Bacon. So this gives us a very sort of natural kind of social network of actors in Hollywood, actors and actresses. But when we talk about influence in the network, we start to see some things that are kind of surprising. So if you compare Kevin Bacon to the actor James Hong, who is a very favorite actor of mine who appears in a number of my favorite movies. So you may not know who James Hong is, though you may recognize him as kind of a character actor in a number of different movies. Kevin Bacon, his degree in terms of acting credits, how many movies he's been in, is only 94 according to Wikipedia, right, or according to IMDb right now. Compare this to James Hong, who has 440 acting credits on IMDb, so that's a significant difference. But when we talk about these kinds of games, the Oracle of Kevin Bacon, we don't really have the Oracle of Hong. Although potentially, maybe we should. But this tells us something about the network, that maybe Kevin Bacon has more influence than James Hong. Again, maybe. This is potentially true because of something about the kinds of movies or the kinds of roles that Kevin Bacon is in. So he's often a leading man, whereas James Hong is, like I said, more of a character player or a character actor. It could also be some bias in the data where Hollywood is intrinsically or has some sort of systematic or systemic racial issue that prevents James Hong from being as influential as Kevin Bacon. But there's some differences here in kinds of influence. When we ask this question about does higher degree mean more influence, then we see an interesting kind of counterexample here where James Hong has a much higher degree than Kevin Bacon, and yet Kevin Bacon seems to be more influential in the network of actors on IMDb. So we can start to talk about other kinds of nodes in terms of influence or how important they are by characterization. So this is a more qualitative kind of view about the kinds of nodes that may exist in a graph. We can talk about hubs and bridges. Now, I'm not really talking about hubs of wheels or physical bridges, but the structure that we see here, where you have a central node and a hub, and it has all these spokes that go out to other nodes, has a sort of network motif that gets reflected often. Likewise, bridges are these nodes that connect multiple communities. So, as I said, in hubs, we can think about a network of individual nodes where they all seem to have one singular node in common, or there's one node that sort of connects all the other nodes. So this is our hub. This node in the middle is our hub node. Whereas bridges, like I said, are these nodes that connect potentially multiple different communities that without these nodes, these bridge nodes, they would not be connected. So I think it's pretty clear that Kevin Bacon in some sense is a hub in the IMDb network, though potentially James Hong is as well. So if we talk about hubs in the social network of actors, we can see that there's clearly Kevin Bacon, there's Irfan Khan and Jackie Chan. These are all hubs within their respective neighborhoods or communities of actors, Hollywood, Bollywood, and Chinese cinema. But how do we connect them? They may be connected by bridge actors or bridge nodes. So Angelina Jolie is a good example of this, where she has been in movies with all three of these actors and bridge all these different communities together. Now, you could say the same thing about Jackie Chan has been in many Chinese cinema movies and in general Hollywood films. So he may qualify as a bridge as himself, which is sort of partially why these hubs and bridges aspects are more qualitative kinds of assessments of nodes. But you can still ask the same kind of question, which node is more important, hubs or bridges? Now again, this is contextual. It depends on what kind of question you're asking. If you're trying to connect multiple communities, then bridges are likely more important. But if you are trying to inoculate a population, then you want to first inoculate the people who are sort of most central or connected to the most people, these sort of hub nodes. But this gives us a bigger question of what does it mean to be important sort of at all? Does that mean highest degree like we've talked about? Does it mean being a hub or being a bridge? Does it mean something about being a hub and a bridge if you are somehow both of these roles simultaneously, that you're much more important? Does it mean having the most shortest paths, so you're sort of the closest to the most people? Or is it something else? Well, we're going to sort of sidestep this question and say we'll define important nodes as being nodes with high centrality, where centrality will become this metric that we use to measure importance. But we really haven't answered the question of what does it mean to be important, because all we've done is created a label for this, but we've not actually said what centrality is. So another example of where centrality is sort of contextual is in the board game Pandemic, where Hong Kong has high degree, meaning that if Hong Kong, from the rules of the game, if there's an outbreak in Hong Kong, that outbreak spreads very rapidly to many other places. Whereas Sao Paulo is sort of a bridge to most of South America, connecting Africa and Europe. So if you wanted to protect if you wanted to protect South America from being infected by one of the diseases in Pandemic, you'd want to prevent Sao Paulo from ever being infected to sort of silo off that part of the continent. So clearly centrality has different meanings here in terms of, could it be influence, could it be prestige or importance, could it be the amount of power that you have over something or the control? Nicely, there's a famous sociologist, Linton Freeman, who in 1979, in one of his papers about centrality in social media, he said, there is certainly no unanimity on exactly what centrality is, or its conceptual foundations, and there's little agreement on the proper procedure for its measurement. So really what this says is centrality can be very, very different and mean different things, and who you ask is going to give you different answers, and what your problem domain is sort of will motivate some of these questions. So when we talk about centrality, we'll talk about four main types. We'll talk about degree centrality, closeness centrality, betweenness centrality, and eigenvector centrality. So these four are sort of the most common that you see. They're all implemented in GEPHI and in Network X and these other sort of standard kinds of graphs, or graph packages, network analysis packages. So you'll see them pop up a lot, and they have some nice sort of intuitive factors that we'll talk about. So I'll not use the Pandemic board here. I'll stick with the risk board that I talked about last time because I have some nice visualizations for this. But I'll use this as sort of our model graph for now, this risk board, because we can see this nice graph of there's clearly different regions. Given that graph, we can talk about degree centrality, where nodes with the highest degree have highest degree centrality. So that means really that we're talking about nodes that can immediately reach the most neighbors. So it's an intuitive kind of feeling that nodes that have just the highest degree, the most connections, are the most central in some way. So in our risk example, that'd be Ukraine with a degree of 6, or China with a degree of 6, the Middle East has a degree of 6, and both North Africa and East Africa have degrees of 6 as well. So we have several different nodes that have very high and in fact the same degree centrality. And we can define this using our adjacency matrix, where we have a binary adjacency matrix. The values represent whether nodes are connected, not necessarily what their weights are. And then for a given node, node D, we can evaluate its degree centrality just by summing up the number of non-zero elements in this adjacency matrix. But then we have this question about how do we compare that number in that graph to centrality, degree centrality in other graphs, where the other graphs may be very different. So this gives us, so to answer that question, we'll use normalized degree centrality, where you take the degree centrality of a given node, and then you divide through by the number of possible nodes you could have. So if we want to know the normalized degree centrality of a node, then we take the sum of all of the incident edges, or its degree, and divide by the number of nodes in the graph minus 1. since that -1 is the node for which we are calculating degree, and this gives us a normalized value between 0 and 1. This is only for graphs where we don't allow self-loops, but you certainly could, in which case you need to divide through by n. The next kind of centrality we'll look at is closeness centrality, where nodes with the most shortest paths have the highest closeness centrality. So what does this mean? It means that if we think of closeness as sort of the inverse of farness, or how far things are, then on average we want nodes that are close to all other nodes in the graph. This is slightly different than degree centrality, because you might have a node that has a very high degree, but is somehow in some sort of siloed part of the network that makes it very hard to get to the other major parts of the network, in which case they aren't necessarily very close, even though they have high degrees. So here we talk about closeness as the inverse of farness, and the intuitive definition here is that we can reach the most nodes and even the most very distant nodes quickly. So from our risk graph, actually Ukraine becomes the node with the highest closeness centrality. It's actually the number of shortest paths from Ukraine to all other nodes in the graph in general is smaller than any other node. So to calculate closeness centrality, we talk about fairness. So we look at what is the shortest distance between a given node, the node for which we're evaluating closeness centrality, and every other node in the graph. And we take the sum of that and then invert it, and we get this idea of closeness. So nodes that are in general very far from all other nodes will get a very low closeness, or nodes that are very close to all other nodes in the network have a very high closeness. And then we can normalize this by dividing n-1 by the farness aspect, or we take closeness and we multiply by n-1. And that makes sense, right? Because if we think about what's the maximum possible closeness you could have, well, that's if a particular node was connected to every other node in the graph. So the hub example I gave you before, where you have one node that's connected to all other nodes, that actually has a shortest distance of 1 to all other nodes in the graph. So that n-1 is the maximum closeness that we could have. I'll note, though, that this is only defined for graphs where you can actually reach other nodes in the graph. If there are nodes that are somehow disconnected, which we'll talk about what that means in a few minutes, then closeness centrality sort of breaks down, because then you might have infinite farness, as it were, because you have no path between two nodes. The third type of centrality we'll talk about is betweenness centrality, where nodes that appear most often in shortest paths have the highest betweenness centrality. So we talk about betweenness centrality generally as a kind of bridge, where many paths must flow through nodes with high betweenness, or rather many shortest paths. So these nodes generally act as like I said, bridges between two communities or multiple communities. So in our risk map, we have North Africa as having very high betweenness centrality, because it connects most of the Americas to most of Africa and Europe, because there's this one node from Brazil to North Africa. So if you want to flow through many of these shortest paths from anywhere in Asia or Europe to Argentina or Peru, you have to flow through North Africa. So betweenness is a little bit more sophisticated than the other centrality metrics that we've talked about, because we have this sum of ratios where we want to talk about sigma st as being the number of shortest paths between these pair of nodes, S and T. So how many shortest paths are there in the graph? And remember, we talked about last week where we can have multiple shortest paths. As long as they have the same length, the same path length, they can be the shortest path. And of those shortest paths, how many of them go through node V, sigma STV in the numerator? So if we look at this ratio, if there's only one shortest path and it goes through V, then this ratio is 1, but you can have multiple shortest paths, only one of which goes through V, so we can have a lower ratio here as well. And we sum this up for all possible pairs of nodes in the graph, except for or excluding the node that we're calculating betweenness centrality for. Now we again have to make some differentiation between directed and undirected graphs here, because for an undirected graph, to get a normalized version of betweenness centrality, we divide through by the number of combinations, the number of pairs of nodes besides V, so that's where you get the n-1 times n-2. We have to also multiply by 2 because the number of nodes, or the number of edges between n minus 1, or between our n minus 1 and n minus 2 other nodes, the directionality there doesn't matter. But for directed graphs, it does. So we lose the doubling factor here that we saw for undirected graphs. All right, the last kind of centrality we'll talk about right now is called eigenvector centrality. And the intuition here is that nodes that are close to other central nodes have a high eigenvector centrality. Or nodes whose neighbors are all highly influential or highly important or central in some way, that node must also itself be central. So a node's eigenvector centrality relies on that value from its neighbors. So in this graph from risk, then the node with the highest eigenvector centrality is the Middle East, and the second highest node is the Ukraine. So to calculate our eigenvector centrality, we set up an eigenvalue problem between our adjacency matrix A and our eigenvalue lambda, and we try and identify some eigenvector pi that squares this equation. Then we can define our eigenvector centrality from this eigenvector pi by looking at the rows of this eigenvector, where each row corresponds to a node in our graph, and the value in that row is that node's eigenvector. We can actually easily calculate this through what's called power iteration, where we initialize pi to some random vector, and then for some number of iterations in a simulation, you multiply a times a normalized pi, and with enough iterations in this sequence, then pi becomes, or pi approaches our true eigenvector, from which we can extract eigenvector centrality values. So why do we care about all this? Well, really this is because nodes that have different values of centrality in these 4 centrality metrics are different kinds of influencers. So to move back to the social media aspect, this is a network of politicians extracted from members of Congress and who they mention and retweet over the past 8 or so years. And we see this network. I have set the node size here based on eigenvector centrality. And we can see that the President of the United States, White House, and real Donald Trump accounts are all highly central in this eigenvector centrality world. Whereas Rosa DeLauro, Rep. Mark Pocan, and a number of these other accounts are also relatively central as well. But that's just looking at eigenvector centrality. If we look at the other kinds of centrality, we see different kinds of rankings. So for degree centrality, if we look at the top 5, so Rosa DeLauro has the highest, followed by Rep. Raskin, and several others. If we look at closeness centrality, we see a similar kind of ranking, but not quite the same. Rosa DeLauro is still on top. Real Donald Trump's not 5, he's now number 4. Kathy McMorris is now newly on this ranking. For Betweenness Centrality, again, Kathy McMorris is moving up, Rosa DeLauro has moved down. We've actually lost Donald Trump here. And for Eigenvector Centrality, we have something very different. So we have the President of the United States, Rosa DeLauro, and real Donald Trump in the top 3, followed by The Hill. It's not at all a politician, but it's a news organization that's highly referenced by members of Congress. These metrics give us different insights into the kinds of nodes that exist in this graph and how they may be different in terms of the influence or role or control over information that they exert within these networks. When we talk about centrality, though, a thing that we want to be able to discuss is sort of this concentration of power. How different is a particular node's centrality metric from the other nodes in the graph? So for here, if we talk about centralization, we can say these two networks seem very different in some way. And network centralization gives us a way to talk about that. We talk about the centrality metric of a given node compared to the other centrality metrics of nodes in that graph. So we can do this for any centrality metric that we have, or even ones that we haven't discussed. But the idea here is somehow in some sort of qualitative way, this one highly centralized node in this top graph is very different, is sort of more centralized, or its centralization is more important than any node in this graph on the bottom, where all of those nodes are probably relatively close in terms of their centrality metric, but this node on the top in the middle is probably very different than all the other nodes in the graph. And we can see this in looking at the distribution of degree centrality, just in these two graphs. So here on the left, we see the most central node, the node that has the highest degree centrality, is only probably about 1.1, maybe 1.2 times the average centrality score for all the other nodes in the graph. But here on the right, the most central node is probably at least double the average degree centrality of all of the nodes in the graph. So that tells us something not just about the node, but also about the graph. So we learn that this node on the right has way more centralization power, way more influence, however influence may be defined here, compared to other nodes in the graph. We can also talk about centralization in terms of the graph. So for the centralization metric, we can say, well, really how centralized is a network as a whole, or how do we quantify this sort of variation in the centrality metrics here? So we find the node with the highest centrality metric for whatever centrality metric we want to use, and then we can say, well, for a given graph, what is the difference between the highest centrality node and all of the nodes in the graph? So here we find that node in the middle has got to be the node with the highest centrality score, and look at all other nodes in the graph, and we calculate some value at being about 18, 18.3, something like that. So this graph is probably relatively centralized compared to this other graph. In fact, we can see that based on the metrics, where the previous graph had a centrality or a centralization metric of about 3 times what we see here, even though we have the same number of nodes. And we can normalize this just as we did with any other centrality metric that we talked about. But the only difference here, to normalize, we need to think about what is the max amount of network centralization that we could see from a graph of this many nodes. So yeah, this max S sub n is what is the maximum amount of centralization we could expect from all other graphs of the same size. So what do we do with that? I mean, oftentimes, though, you can think of this graph, this very clear hub and spoke graph, as having the maximum centrality score. So this is probably the most centralized network you could imagine. So for this number of nodes, it's about 41. So then we can say, if we compare this network, normalized centralization metric for the graph is about 0.4, 0.45, whereas compared to this graph, which is about 0.1, 0.14. So we can see that this graph here is much more centralized than this graph here, even compared to other networks that have similar number or the same number of nodes. So those are some metrics for doing influence and importance. Now let's talk about subgraphs and egocentric networks. So now that we've talked about influential nodes and extraction of subgraphs, now let's talk about interesting ways where we can build subgraphs in some sort of meaningful way, besides just looking at the neighborhoods of influential nodes. To do this, we'll talk about 2 different ways of creating subgraphs, specifically partitioning and clustering, and then we'll talk about the connection between clusters and communities and ways to do community detection in the social media graphs that we are generating. So first, to distinguish between partitioning and clustering, you may think of them as sort of synonymous, but we will talk about them in a distinct kind of way, where partitioning is explicitly separating a graph into a predefined number of separate, equally sized parts. And critically, we want to minimize the number of edges that we have to cut in order to assign a node to a given partition. So why might you want to do this? So generally, the approach for partitioning is meant for decomposing a graph into manageable subgraphs that you can then perform subanalysis on, or model, or apply some sort of algorithm to in a way where the communication between partitions is minimized. So if you're thinking about sort of large-scale clusters for computation, you want to be able to focus on specific subgraphs in the network, because maybe you can't fit the whole network in memory for a single node, and you want to be able to process everything on that small subgraph without having to send a lot of communication or send a lot of messages between that partition and other partitions. Now, in contrast, clustering is you generally don't know the value of k, or you don't have a hard limit for k beforehand, and the clusters you generate are meant to be similar, or sort of represent similarity where similarity has a real-world meaning. Maybe it's party affiliation, like here, this graph that I've shown you before, where the red nodes are grouped into a cluster for Republicans and the blue nodes get grouped into a cluster for Democrats. Or it could be other kinds of groupings as well, from geographic to age or sort of some other sort of demographic or topical model. But the clusters that we generate here are often affiliated with communities of some form. When we talk about comparing clustering and partitioning, though, generally the purposes are different and the kinds of information you need or expect to have beforehand are different. So for clustering, generally the purpose of this is for analysis, and we want to be able to either zoom in on a particular cluster, understand what some group of people or group of nodes are doing, where all these nodes in the same cluster or community sort of behave similarly. We want to zoom out and say that, well, all nodes in this particular cluster or community behave similarly, so we will just sort of abstract them away and say all these nodes actually are the same kind of node. Partitioning, on the other hand, is about working on these blocks where you want to create some sort of clear partition and then do some sort of processing on each partition. This means that for clustering, you generally don't know the number of blocks beforehand, that you can have insight, like the number of political parties in the United States, or the number of states if you're doing geolocation, but you don't have to preload the algorithm or whatever method you're using for clustering with that number. Whereas partitioning, you explicitly have to specify some value of k, or how many partitions you want. The number of, or rather the size of the blocks is generally unspecified in a clustering algorithm. I don't necessarily tell the algorithm that, well, X number of nodes must be in cluster 1, X number of nodes must be in cluster 2. For partitioning, though, part of the goal for partitioning is to make partitions of equal size. So you have some idea of some constraint or limit around the size of a partition. Criteria are sort of various across both, and constraints are pretty lax in terms of clustering. We don't necessarily need to require some sort of difference in the clusterings or require clusters to be of the same size. Partitions, though, we generally have that kind of constraint. We want partitions of equal size with a number of other sort of factors that are driving us. So in going back to partitions versus clusters, let's talk about how we actually might do partitioning. So the general task here is we have some graph of vertices and edges, and we want to divide the set of vertices into k sort of equally sized subgraphs. And generally these subgraphs or these nodes have the same size. So we get k equally sized chunks. And for partitioning, a node exists only ever in one partition. You don't have nodes that show up in multiple partitions, but this is a constraint that we don't have in clustering. So you can have fuzzy clustering where an individual may exist in multiple clusters simultaneously. That's not the case in partitioning. And then finally, the more interesting kind of constraint here for partitioning is we want to minimize the edges between VI and VJ. And that's where a lot of the complexity comes in. So like we can arbitrarily create equally sized chunks of nodes, and we can do so in a way where there's no intersection between these chunks, but minimizing the number of edges between these chunks of nodes or these partitions of nodes, it can be computationally complex. And we can talk about this in terms of complexity, where if we are trying to divide a network into a set of k equally sized nodes, then what we have to do is check every partition, potentially check every possible partitioning of size k. So even if we're doing the simplest, we're doing like bisection, where k equals 2, this is still going to be an exponential kind of question, or big O of 2 to the n, where n is the number of nodes. Because you can think about this as, well, we have to check every single possible partition, so we can rank which partitions are the best. And if we don't check a given partition, we don't know where it goes in the rank, so we can't necessarily build this ordering correctly without checking them all, which means that we have to do every set or around every set of this possible assignment of a given node to one of two possible partitions. So from a computational complexity perspective, this graph partitioning problem is known to be NP complete, meaning it's difficult to generate good solutions, but it is relatively easy to check that a solution is a correct solution in polynomial time. So because of this complexity, generally partitioning algorithms are built around heuristics. So rather than going into a lot of detail about how you can do this exactly, I'll give you some heuristics for doing clustering, or excuse me, heuristics for partitioning. We'll talk about two main ones. One is the idea behind graph bisection using the KERNIGHAN-LIN algorithm, and then I'll talk about how to use the KL algorithm to build up other partitions. So first, just a real quick definition. Graph bisection is this partitioning of a graph into two equally sized partitions. So this is the k = 2 problem. So a popular way of doing this is the KL algorithm, or the KERNIGHAN-LIN algorithm. Originally, the complexity for this is n cubed, but nicely it can be reduced to complexity on the order of the number of edges in your graph. The general intuition here is that for a given partition, or a set of split of nodes into two different sets, for each pair of nodes in the different partitions, we can swap them. And if the swap reduces the number of edges we have to cut for this partitioning, then that's a good swap. So we can look at this graphically. So here, this is our graph. A is connected to F, G, and B. C is connected to G, D, and to G and D, etc. And we can generate some sort of initial random partition where we say A, B, C, and D are in one partition, E, F, G, and H are in the other. And now what we want to do is sort of modify these initial partitions in a way that reduces the number of edges that we cut. So first we select some pair. Here we select D and G, and then we check, does swapping D and G, putting D into the other partition and G into the other partition, does that reduce the number of cuts? Graphically, we see that it does. So that's great. Now we move to another pair, C and F. We haven't tested this one yet in this iteration, so now let's swap them. Does it further reduce the number of cuts? And in fact, it does. We went from 2 edges that were cut for this partitioning only down to 1. And we can continue to do this, testing all pairs, and then iterate through this process until we are no longer able to reduce the number of edges that are cut by our partitioning. So you can keep going through this in a relatively straightforward way. Now, that's only for k = 2, this bisection partitioning. So if we want to partition into larger values of k, we can still apply the graph bisection problem and say, well, first let's split it into 2 pieces. So here's maybe the clearest cut between these, what's relatively clear 5 communities or 5 clusters. And now we want to further bisect these 2 groups. And then you could do some test to see if, well, do we massively increase the number of edges that we cut with this bisection on the left? We can either keep that or not. And we can check the same thing on the right and either keep that or not. And we can keep going and keep going to create an arbitrary number of partitions within this graph. So we won't deal too much with graph partitioning. You certainly can. Like I said, if you happen to know or come into the problem knowing what the k value you have is, and you want to enforce that k value, so say you are going to use partitioning to do political party affiliation or anything that falls into some explicitly set number of classes, you could use graph partitioning for that. If you want to understand something about communities, then we'll focus on graph clustering. Again, the idea here is we're grouping nodes into sets of similar vertices, where similar has some sort of meaning that either we know beforehand or we want to extract in some way. Like I said, the example, that sort of general example or the go-to example is this political affiliation aspect. So we define the partitioning task above as trying to set or construct equally sized groups with no overlap that minimizes the number of between partition edges, or the number of edges that we must cut for the partition. For clustering, it's similar. We have that same minimizing the number of edges between clusters. So this is the same goal for partitioning. And we want to maximize the number of within cluster edges. So this is the idea here is that nodes that are very similar will have lots of edges between them, or groups of nodes that are very similar will have many edges between them. So we want to maximize this number of within cluster edges. We actually have an objective function that is often used for doing this. It's called modularity. There's a particular equation for this. that I'll break down now. So it's the sum of the number of edges that you see in a given network, where Aij is the adjacency matrix that we've seen before. And we subtract off what the likelihood of seeing two random edges between two given nodes are, and then we multiply by this del function, which is whether x sub I and x sub j are within the same cluster. And we want to maximize this value. So again, k sub I is the degree of a given node. M is the number of edges in the graph. So these k sub I over 2m and k sub j over 2m, really what that says is what is the likelihood, or how likely is it that two given nodes, k sub I, or two given nodes I and j, are going to randomly have edges between the two of them. So if you have two like extremely high degree nodes, the fact that there is an edge between them is maybe not hugely interesting. But if you have two nodes with very few edges between them, or very low degree, then if there is an edge between them, that potentially has a lot of information. So we want to capture that. So as I mentioned, let's break this down a little bit. The del function is 1. It's this indicator function that gets the value of 1 if and only if x sub I and x sub j, these two nodes, are in the same cluster or the same group. This a sub ij is from our adjacency matrix. It gets a 1 if there is an edge between these two nodes. And then, like I said, this k sub I over 2m times k sub j over 2m is the probability of having some random edge between these two nodes. So the whole idea here is that adjacent nodes that have few edges ought to be in the same group. Now that's the objective function. We can talk about like an example of this. So here we have the same nodes, same edges, and we have two ways of labeling them into two separate clusters. On the left, we have what appears to be a more sort of intuitive view, where we have the three nodes on the right get in one cluster and the three nodes on the left get in another cluster. On the right-hand side, we have 4 nodes in the left cluster and 2 nodes in the right cluster. We can actually calculate what the modularity is here. And on the left-hand side, we see this 5 over 14, or 0.357, is higher than this 6 over 49, or 0.122. So we can say from a modularity perspective, this grouping on the left, or this clustering on the left, is superior to this clustering on the right. And you could have sort of qualitatively evaluated that just by viewing this, but now we have a metric that we can optimize. So good cluster assignment mechanisms try to maximize this modularity function. But exactly maximizing Q is a very computationally complex process, again, known to be NP complete because we have to evaluate every single possible grouping. In some cases, even more complex than the partitioning case, because the partitioning case we have a known pre-specified value of k, and how many partitions we have. Here we don't necessarily know how many clusters we have, so this is going to be a very difficult thing to do exactly. So instead, oftentimes, or to the vast majority of the time, we rely on heuristics for doing clustering. So now we'll talk about some heuristics for this clustering, and specifically we'll use heuristics around community detection, looking at 3 different methods: label propagation, GIRVAN-NEWMAN detection, and the Louvain method. So I'll first go through the intuition for each one, and then the details for each method. So for label propagation, this is supposed to be a relatively simple message passing algorithm that uses voting to understand or identify what a community is. So the simple algorithm here is that a node takes the majority label of its neighbors, and this is an iterative approach, so you keep iterating on potential clustering until some stopping condition is met, and in each iteration all the nodes look at their neighbors and take the majority label from their neighbor. So a very simple algorithm. Like I said, it's got some stopping criteria, and as long as we haven't hit the stopping criteria, we're just going to, for every node, we'll take the label that maximizes the number of times that your neighbors have that label. So you start the label propagation algorithm by randomly assigning all the nodes in your graph to a random cluster, or in this case, a random color. The algorithm proceeds one iteration, randomly breaking ties, and now we have a new clustering with hopefully fewer numbers of clusters. We proceed one more iteration and we see even fewer numbers of clusters, and now we have some idea that we're converging towards a consistent clustering. And then after several iterations, we've hopefully arrived at a stable or converged at a stable clustering of the graph based on just looking at who my neighbors are majority-wise. There are some issues with label propagation, namely oscillation. So you could imagine, well, in this iteration, all of my neighbors are in one cluster, but since all of the nodes are sort of figuring out what their clusters are, or cluster assignments are simultaneously, you can end up with this loop where they go back and forth in the same, or between two, they oscillate between two potential clusterings. And this is where your stopping criteria would come in to end this, or you'd identify some heuristic that would identify this oscillation and then stop. So Network X has a more sophisticated version of this algorithm that prevents these kinds of oscillations, but that's the general idea, that at any moment in time, a given node takes the majority cluster assignment of its neighbors. A key point to know about label propagation, and in fact most clustering algorithms, is that since we don't necessarily know what the ground truth is for clusters, multiple runs may produce different cluster assignments. And that's not necessarily a weakness, but is a thing you have to be aware of when you're running these clustering algorithms. The next method we'll talk about is GIRVAN-NEWMAN, which is, the intuition here is that it uses centrality to identify communities. It uses centrality in a slightly different way though, so what we've talked about in terms of betweenness centrality for nodes, GIRVAN-NEWMAN uses betweenness centrality of edges, and then it removes these edges with high betweenness centrality. And whatever's left over are likely to be sort of clear clusters. So you can imagine in this graph on the right, all these edges here that connect this bridge to this like large chunk of nodes there. If you removed all of those edges, you'd be left over with a number of these low betweenness edges, and this what's clearly a sum community. That all of these edges here have some much higher betweenness centrality than the edges in this sort of core cluster. So by removing them, we nicely separate this community from this other community. And again, we have, since it's some heuristic, we have some stopping criteria that will stop removing these edges once we've maximized some sort of modularity. But since this is a heuristic, we know that there's going to be some possible issue with local maxima that we see here. Like this is a standard example of a social network called Zachary's Karate Club. And if you look at the modularity increase by looking at, as you remove edges, you see there's after removing 10 or so edges, you get this big bump in modularity. But then you see a drop. And if your algorithm stops there, because it's found, okay, now I've removed an edge, and removing this next edge reduces the modularity that we're trying to maximize. If we stop too early, then we miss out on this higher quality clustering that we get if we were to have continued to remove edges. So again, Network X has a nice implementation for GIRVAN-NEWMAN, which you can use. Note that it's not very fast on Network X, so if you have any sort of non-trivially sized graph, it can take a while to run this approach, or to run this algorithm, but it is there and it is available for you to use. And the last method we'll talk about is the Louvain method. It's this iterative two-phased algorithm that's used in GEPHI, and that gets discussed in the Blondel paper that I've given you. So the idea here is, in phase one, we merge nodes into groups that are at least locally optimal for our modularity. And in phase two, we merge all these clusters into metanodes and then use those metanodes to evaluate some sort of global modularity. So in phase one, we do this random assignment of every node into some unique cluster, and then we check for every node, we check all of its neighbors to see if adding these two nodes together into a community increases our modularity. Once we've done that, we can merge these neighbors into this community with the maximal modularity. And now we are set up for phase two, where we take all nodes that are in the same cluster, or same community, and merge them into a single metanode. Then we can look at connections between communities or connections between clusters, merge those edges between clusters into a single weighted edge, and then reevaluate the phase 1 version, but rather than looking at all nodes in the graph, we only have to deal with these meta cluster level nodes. We can continue to do this until there's no more gain in modularity, and then we have potentially optimal clustering. So here we have this graph. We can see starting on the top left, we have a random assignment of nodes to clusters. On the right, we've identified some intermediate clustering that we think works at this local level. Then we merge all of these clusters into meta clusters or meta communities, and then we do some reevaluation of modularity on these meta clusters, and we get just this 2 potential communities. And then we use that to reassign or to propagate through our cluster assignments to all the nodes in our graph. And now we have ended up with clustering in 2 particular clusters or 2 communities here. So now you have some understanding about how the modularity feature in GEPHI works. So if you load some network in GEPHI, you click the modularity button, it'll tell you after it runs how many communities it's identified. That's this number of communities here. What's the modularity metric it came up with, and what the distribution of the cluster sizes are, or community sizes are. And you can use this information to color your nodes on your graph in an interesting way. So if you go up here to Appearance, you click on the Color button, you select Partition by Modularity class, and you apply this coloring. Now you get this nice coloring of something about community structure that's built into whatever node, or that's somehow extractable from whatever network you're doing your analysis on. Here, this is the network of politicians that I've discussed, and you can see that there's some kind of structure here with a clear green community, pink community, and a blue community. And if we sort of zoom in on this, we can see that the green community is a set of maybe more moderate conservative politicians, and the blue community is a set of other conservative politicians, and this pink community is a set of liberal politicians. But again, this is maybe not what you anticipated. If we were only talking about party affiliation, you would expect to see 2 clear clusters here instead of seeing 3 main clusters. So note that you have to understand something, or you have to potentially apply some sort of qualitative evaluation or analysis to what these clusters mean to understand or interpret them in a reasonable way. All right, so that wraps us up for week 2. We've defined centrality metrics and used them to identify influential nodes. We've talked about egocentric networks and other kinds of subgraphs, connected components, and cliques. And then we've talked about several methods to identify communities of nodes in graphs, from GIRVAN-NEWMAN to Louvain to potentially bisection if you know the value of k beforehand. That'll be the end for Module 3. If you have any questions, feel free to post them on the discussion forum, where I'll be posting discussion questions as well.